So, hi, I'm David Perpetuini from University of Chieti Pescara, and today I will talk to you about the deployment of machine learning in neuroimaging for the early detection of the Alzheimer's disease. The Alzheimer's disease is a kind of dementia which is characterized by memory impairments that become more consistent with the progression of the disease. And it is also accompanied with some impairments in executive abilities. Moreover, the disease is characterized also by plaques constituted of self-assembling peptide known beta-amyloid. This beta-amyloid is associated with cerebrovascular alterations. So it suggests that the AD is also accompanied with a vascular damage. This theory was also confirmed because some alteration in the peripheral circulations were assessed by means of laser Doppler flowmetry and also by means of photoplethysmography. In particular, with the photoplethysmography, it was demonstrated that the sensibility of the aortic is related to the white matter relations in AD, and also a model to support the diagnosis of the mild cognitive impairment with photoplethysmography was developed. So, actually, there's no biological marker indicative of and selective for the differential diagnosis of the Alzheimer's disease. For this reason, some cognitive tests were developed to assess these initial memory failures for the AD diagnosis. The hypothesis is that we can use neuroimaging techniques together with these tests to see if it is possible to increase the capability of this test to detect the pathology. However, it is important to preserve the interaction between the doctor and the patient, because also in the interaction, it is important to perform the diagnosis. So all ecological neuroimaging techniques could be used to Disea. Particularly to evaluate the central brain activity, we use the functional near infrared spectroscopy and electroencephalography, and to assess the autonomic nervous system activity, the infrared thermography is a suitable tool. So we want to see if it is possible to apply machine learning approaches to these neuroimaging signals in order to support the diagnosis of this dementia. FNIRS is a functional near infrared spectroscopy, and is an optical technique that is able to collect the hemodynamic changes in the cortex. Thanks to the employment of two different wavelengths, it is able to measure the variations in the oxygenated and the oxygenated hemoglobin related to the neuronal activity. So this technique is portable, is cheap, and is also robust to motion artifacts. So it's a very useful tool for this kind of applications. So first attempt to use the FNIRS during the administration of this cognitive task was performed employing some tests that are usually used in clinical practice for the AD identification. Specifically, we have the clock drawing test, which evaluates the visual spatial abilities. We have the digit span test, which assesses the short-term memory impairments. The Corsi block tapping test, which is employed to estimate the visual spatial skills. And the main issues in using neuroimaging tools in these such an ecological protocols relies on the data analysis, because for the neuroimaging data analysis, you need to know, for the canonical data analysis, you need to know the start of the activation and the duration of the activation. But actually, we don't have either the start and activation and the duration of the activation. For this reason, we employed complexity matrix, that is the sample entropy, and the multiscale entropy, which allows to measure the predictability of the signal, and so also the brain activity associated to the execution of these tasks. And this complexity metric of the FNIR signal was used to feed a linear multivariate analysis used in a machine learning approach with a cross-validation framework to assess if it is possible to discriminate Alzheimer's disease patients from healthy controls. The results demonstrated with the descriptive statistics that FNIRS is able to assess differences in the brain activation related to the execution of these tasks in Alzheimer's disease with respect to healthy controls. And if we perform a classification with a machine learning approach based on the scores of the test that we use, we can see that the clock drawing test has an error under the curve of 0.9, which is quite high. And we also see that the FNIRS sample entropy deliver an error under the curve over 0.665, and for the clock drawing test is lower with respect to the scores, but for the other tests, we can see that there is an improvement of the detection of the Alzheimer's disease, employing also neuroimaging tool. Together with the FNIRS, we can also use the electroencephalography, which is able to measure the brain electrical activity by measuring the currents within neural sum. The EEG was used together with the FNIRS because these two techniques are quite important, because the EEG can measure the electrical brain activity, so it's a direct measure of the brain activity, whereas FNIRS measure the hemodynamic associated with the brain activity, so it's an indirect measure of the brain activity. Moreover, the employment of the two techniques together can deliver information on the neurovascular coupling, which could be compromised in Alzheimer's disease patients. So we used this multimodal approach during the execution of two tests, that is the Ray-Osterried complex figure, which is divided into two phases. The first one, the patient has to copy a figure, and after 15 minutes, he has to recall the figure, so draw it again. During this, the meantime between the copying and the recall phases, to the patients was administered the Reben progressive matrices, which are used to assess visuospatial ability. So, visuospatial abilities. In order to assess the brain activity, we also use the sample entropy of the FNIRS and EEG signal, but also we wanted to explore the neurovascular coupling between the electrical and the hemodynamic activities. So we used also the conditional entropy, which is indicative of the information needed to describe the outcome of a random variable given the value of another random variable. So we used the variance of the FNIRS to explain the EEG. So this is the results of classification, cross-validated classification performed using a linear model. And as we can see, we are able to discriminate the AD patients from healthy controls with both FNIRS and EEG, but evaluating the neurovascular coupling, hence coupling the EEG with the FNIRS, the performances of the classifications increased significantly. During the administration of these tests, we also evaluated the autonomic activity of the patients. Particularly, we used the infrared thermography, which is able to measure the cutaneous temperature of a patient. This procedure is sensitive to the autonomic state of the subject and can be indicative also of the psychophysiological state of the patients. Since it is completely contactless, non-invasive, it can be easily used in a clinical context, such as the administration of clinical tests. And actually, it was demonstrated the data analysis of the infrared thermography data is based on the evaluation of some responsive regions on the face of the patients. And one of the most responsive regions is the nose. Obviously, it's not the only one, but the nose is considered one of the most responsive regions. And as we can see, the nose temperature has a modulation related to the execution of the task. And evaluating also in this case some frequency metrics and the sample entropy of the thermal signal, we can see that we are able to discriminate the patients from healthy controls. However, the question related to these studies is about that all the findings are related to the response of the task, so they are task related. And maybe it could be worth to investigate the possibility to discriminate AD patients from healthy controls using resting state data. So during resting state in basal condition. So we evaluated also in this case the central nervous system activity by means of EEG and FNIRS, and combining the EEG FNIRS to evaluate the neurovascular capping, but also we wanted to evaluate peripheral circulation impairments by means of the phasal temperature time curves by means of infrared thermography. The first attempt is related to the evaluation of the EEG microstates, because we know that that EEG was found to be comprised of a small number of topographic classes, at least 5, that are stable for 10, 100 milliseconds, and after that they switch to another class. And these 4 topographic maps are supposed to be correlated to the brain's resting state networks activation and inactivation. So we wanted to evaluate if it is possible to extract some metrics from the EEG microstates to discriminate AD patients from healthy controls. So it is possible to see that not all the metrics are able to discriminate these two populations, but some metrics are able to differentiate AD patients from healthy controls. And employing these metrics in a linear model, cross-validated, it's possible to deliver a classification of the AD patients with narrow under the curve of 0.7. After that, it is easy to suppose that we can also use more canonical analysis for the EEG and also FNIRS data analysis. That is to evaluate the global EEG power in some frequency bands of the EEG signals, and also to evaluate the power of the oxyhemoglobin and deoxyhemoglobin during the resting state. As we can see, during the resting state, the EEG and the FNIRS alone are not able to discriminate in a very good manner the two populations that are under the curve are quite low. But maybe the evaluation of the neurovascular coupling could deliver more information. In fact, in order to evaluate the neurovascular coupling during the resting state, we considered the frequency band, the EEG frequency, the EEG power in such frequency bands, and we evaluated the principal component analysis, considered the normalized first component. After that, in order to have a same temporal resolution of the FNIRS signal, because we know that the EEG signal is an electrical signal which is faster with respect to the hemodynamic activity. So we convolved the electrical activity with the hemodynamic response function, and after that we used a general linear model approach. This kind of approach is kind of widely used in the fMRI, but with FNIRS is not so used. I mean, the employment of the GLM to predict the EEG activity from the FNIRS signal with a general linear model. And so we used as independent variable the FNIRS signal from long channels. In order to reduce the physiological confoundings, we also use some short separation channels. And as the dependent variables, we used the EG power band convolved with the hemodynamic response function. And we can see that we can increase the capability of these neuroimaging techniques to discriminate the AD patients from the FNIRS signal. And the metrics employed are hence the coupling between some frequency band of the EG signal and the hemoglobin forms, that is oxyhemoglobin and deoxyhemoglobin. In these cases, we reached an R under the curve of 0.9, which is quite high. Finally, we decided also to investigate the capability of the infrared thermography to assess the Alzheimer's disease, to discriminate Alzheimer's disease patients from healthy controls during resting state. In this case, we evaluated some frequency metrics, that is the power spectral density in specific frequency bands, that is the metabolic, myogenic, respiratory, neurogenic, and cardiac bands. And we also used a supervector machine with linear kernel in a cross-validated manner. And we employed only the frequency bands that show some differences with descriptive statistics. And we found an R under the curve of 0.77, which is quite high, and maybe demonstrates the impairment of the peripheral microcirculation in Alzheimer's disease and the capability of the infrared thermography to assess this impairment. So finally, we can say that the neuroimaging techniques and machine learning procedures can be used to support the Alzheimer's disease diagnosis. Particularly, it can be used during the administration of clinical tests in order to help the physician, doctor to perform the diagnosis. But also, these techniques could be used during resting state in basal condition to assess dysregulated electrical brain oscillations, and also impaired neurovascular coupling, and also impaired peripheral circulation. Obviously, it could be worth to investigate whether the combination of peripheral information and central nervous system information could deliver a more reliable discrimination of these two groups. Thank you for your attention.